Hello everyone. For this tutorial video, I like to talk about higher order derivatives of partial derivatives instead of single variable derivatives. We remember from single variable derivatives that higher order derivatives are derivatives of derivatives, derivatives of them, and so on. The same exact definition is true for multivariable functions. What we saw for the first order derivatives, we had two separate derivatives because we had two separate variables, or three separate derivatives if we have a function of three variables instead, etc. So this same problem comes up in higher order derivatives as well, because you can differentiate the derivative with respect to either x or y. There's not one set variable that works for them all. We would denote higher order derivatives with a capital delta, just like the first order derivatives, but we could condense the notation once we multiply out the symbols and functions like so. So the convention in the denominator is to write the first order derivative at the rightmost end, the derivative of that to the left of it, the derivative of that to the left of that, and so on. So with that out of the way, if we were given a specific function and asked to find its second order derivatives, we would do this by taking the two first order derivatives, like we did in the last video, and then taking the derivatives of them, making sure to pay attention to A, the variables requested, and B, the exact order you do it in. Interestingly enough, the derivative with respect to x of the derivative with respect to y, and the derivative with respect to y of the derivatives with respect to x both give you the same exact result. And this actually happens so often that there is a theorem to predict it, called Clairaut's theorem, which says that if a multivariable function is defined on a disk, capital D, and it is at the points a, b, then it follows that if these two derivatives are continuous at that point, these derivatives are exactly equal to each other, which makes sense because remember from Calc 1, the mathematical definition of continuity is that the limit of the function is exactly equal to the value of the function at that point. So it follows that if these two derivatives are equal to the value of the function at the point, then they must be equal to each other by basic logic of what equality means. Before we discuss differentials and the chain rule for multivariable functions, I'd like to talk about higher order derivatives than second order derivatives, which get even more messy. In particular, we would use the same notation, so the capital deltas, where the numerator is the function and the denominator is the variable you are taking the derivative with respect to, and then condensing the derivative notation as appropriate. And we can also see, with some clever thinking, that we can condense the third order derivative as the leftmost point multiplied by the two variables you are differentiating. And so, it can be thought of as a sort of second order derivative in that sense. And Clairaut's theorem will hold for it as well. So this means that no matter how many times you take the partial derivatives, as long as the exact number of times for each variable is equal between both calculations, then the results will always be equal, and the order does not matter. Now that we have shown how higher order partial derivatives work, we can discuss multivariable differentials next, which are similar to Calc 1 differentials. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.